What follows is a very brief video lecture, a brief introduction to the gravitational force. Involved in the gravitational force equation is a so-called universal constant. It's called the universal gravitational constant. You don't have to know that. But that's the value that's present in all gravitational force calculations. I show an object whose mass is m1, separated center to center with another object of mass m2 by a distance r. That arrow represents the pull on m1 by m2. This arrow represents the pull on m2 by m1. By Newton's third law, those pulls are equal. And so we symbolize the value of each pull with the same letter F. How do you calculate F? Well, that's the equation there, the most important equation perhaps in this chapter, and one of the more important equations since the dawn of time. The force of attraction is proportional to the product of the masses divided by the square of the distance between them. And there's a constant multiplier. Let's work a really simple example. Suppose one object has a mass of 600,000 kilograms. Maybe this is an asteroid. 6 times 10 to the 5th kg. The other one has a mass of 8 million kilograms. 8 times 10 to the 6th kg. Let the separation between the two of them be 10 meters. And now let's calculate the force using the equation in the box. The first parenthesis is G. Then there's the mass m1, the mass m2, and then r is squared in the denominator. You have a product of a kg times a kg upstairs, gives a kg squared, but downstairs in the denominator, there's a kg squared. It cancels the other kgs. And then you have in the parentheses here a meter unit, m. That doesn't stand for mass. That's meter. And it gets squared. It cancels the meter squared that's there. Final result is 3.20 newtons. Huge masses exert 3.2 newtons of force on each other. Well, that shouldn't amaze you and tell you here how much a newton of force is. We may have mentioned it in our study earlier of forces, but I'll mention it again. If you want to experience what a newton of force feels like, put a cube of butter in your hand. It's about 1/4 of a pound. It takes 4 cubes to make a pound, right? And that's not very much force you're experiencing as you heft or hold or support that cube of butter. Push on somebody with that force, no effect. That's a pretty small force. It shows that gravitational forces are pretty weak unless you're dealing with objects, well, the size of, or the mass of the sun, for example. That's 10 to the 30th kilograms. And the size of the Earth, which is about 5 or 6 times 10 to the 24th kilograms. Then the gravitational force is substantial and meaningful, but not with masses as small as even 8 million kilograms and 600,000 kilograms, separated by what, about more than 33 feet, or about 33 feet. All right, there'll be more to say about the gravitational force in other lectures.